So in the next slide, we can see the minimum uptime, minimum downtime, and Q constant. Like we have to maintain all those things. Like when a generating unit is in already off condition, then its unit shouldn't take in on condition immediately. We need some time to on this generator. And when generator is in on condition, then it can't be in off at that time. We need some time to the generator in off condition. So this is known as minimum downtime. Crew constant means how many labor or how many crew members there in the power plant to maintain these things. And another part is like the maximum and minimum limit of the generating units. Every generating unit has some limit. That means minimum generating power amount and the maximum generating power amount. So here we can see the constants. So such as the equation to, this is known as load balance equation. That means whatever the generator is on condition meets the time varying load demand. And in case of the initial status of the generating unit, this is also the important thing, because we have to maintain the initial status. Means if when any generator is in on condition, we can't keep this generator in off. And if when any generator in off condition, we can't keep it to the in on. So we need some minimum downtime and minimum time. So we have to record the initial status of each power generating units and availability constants of the power generating units. So in the second slide, we can say the optimization. So what is the optimization? We need to optimize those things. So basically there are the three types of the optimization, like stochastic optimization, heuristic optimization, meta-heuristic optimization. So within three optimization, here I will show you my own research experimental data also regarding this. So we have to know the what is the basic of these things. So basic of the optimization. Like in case of the stochastic optimization algorithm, we can say that is a random process of the stochastic optimization techniques. That means we can take the random data, we can collect the random data, and then we upgrade this optimization into the heuristic nature. So heuristic nature optimization is basically, it is a trial and error method of the optimization. So trial and error method means we can take some data and collect some data, and then we trial, and if get some error, we just eliminate the system. And when we upgrade next one, that is the meta heuristic optimization. So in case of the meta heuristic optimization, this is the problem independent. So we can easily uh, take our optimization in local search area as well as the global search area. So those optimization techniques are also used for not only for the power generating station or power distribution, or how many times generating, how many amount of power, how what are the amount of power, what are the megawatt. Not only like that, we can also find out the fault from, if anywhere the fault occurs in transmission line or distribution line or any power sectors, then we can easily identify the fault or location of the fault by using this optimization technique. So there are, in this slide we can see that there are the several types of the optimization technique, and we can get those things. So what is the exploitation and exploration? Exploitation basically is the local search capability. When our local area is the limited and is a local area, then we can consider that is a exploitation. And when it is in the global area, then it is known as the exploration. So in this slide, we can easily see what is the exploitation and what is exploration. That means here, this is our first zone area or area 1. And we can take this is our area 2. So here, when our optimizer is searching for a fault condition or the better condition, then it can find that this peak is in highest peak within this area. So our optimizer find this peak as the highest peak within this area. So this is known as local optima or local minima. But when we consider the global minima, so at that time, this is not our highest peak. So our optimizer again searching the peak, which is the highest peak in the total area, not only local, it will be in the, but also it will be in the global. So in case of the global in this picture, we can find this peak as a highest peak. So this kind of the search is known as the global search. So here also in this graph, we can see this is the local minima and this is the global minima. And what are the scope of some optimization in the power system? We can see easily here. There are the several types of the optimization like harmony search optimization, particle sum optimization, BAT-inspired algorithm, artificial bee colony algorithm, and there are the several types. But there is always a scope of improvements in existing optimization algorithm. Okay, so due to this, in my research, I am showing my research, like due to this, we just upgrade optimization techniques. And when we upgrade the optimization technique, then we have need to maintain something like how to effectively avoid the local optima and how to preferably combine the advantage of the different optimization algorithm, how to effectively set the parameters of an algorithm, what are the effective iteration stop condition, how to effectively regulate its develop the direction and so on. So these all are the questions we need to make this. So as we see in the previous slide, like the local search algorithm and the global search algorithm, so we mixed those optimizer and we can make as a hybrid search algorithm. Because if we make a hybrid search algorithm, we can see our system can search the local position also as well as the global position also. So we create here a hybrid search algorithm. So the existing algorithms are chaotic search and existing local search algorithm. In literature review also you can from Google also you can take this, that chaotic search and optimizer algorithm is a local search algorithm, and Harris-Fox optimizer, sine cosine algorithm and slime mold algorithm is basically the global search algorithm. But when we merge these two algorithms, local search and global search, you can use any kind of software like MATLAB, Python, this language we can use for merging this. Okay, so I am showing my one of my research work, like I merged this local optimizer to this kind of global optimizer and make own hybrid optimizer, make some own hybrid optimizer like here, and I implement those hybrid optimizer to generating station, power generating station, to identify that which generating unit should be kept in how many hours and which generating unit should be kept off for how many hours. It will, and including the renewable energy sources also. When we include the renewable energy power generating station, that means solar. Here in my research, solar is included, solar power station. Okay, we combined with the thermal power generating unit. So at that time, what will be the cases and how we can off our generator for some time and we can generate from the solar panels, and how it is feasible for us and what are the uncertainty. Every time solar panel can't give us the same amount of megawatt power because it is there are the solar uncertainty, because it depends upon the weather also, moisture also, the several types of the uncertainty. So how we can manage those things? So I will show you in upcoming slides those things. Okay. So here I used MATLAB. Basically, I personally used MATLAB software to merge this to and make the hybrid optimization technique. And these optimization techniques are the meta heuristic. In previous optimizer, I already showed you like the three types of the optimizer are there: stochastic, heuristic, and meta heuristic. Basically, I preferred meta heuristic as it is the problem independent. So here we can see I named this optimizer like CHHO, that is chaotic Harris-Fox optimizer, and this one is the chaotic sine cosine algorithm. This one is chaotic slime mold algorithm, and again I combine these two optimizer, that is hybrid chaotic Harris-Fox optimizer with sine cosine algorithm, and hybrid chaotic slime mold algorithm with sine cosine algorithm. Okay, so those are basically we can also use nowadays. Maximum we use that artificial intelligence. So in artificial intelligence part, that AI, so there is also include a optimization part. So artificially how artificial intelligence meet those optimizer, we can see here that in Harris-Fox optimizer, like Harris-Fox is a bird. So how we can see that the cooperative behavior of the chasing style of Harris-Fox, nature inspired, this is a nature inspired optimization technique, and we make the mathematical equations which mimic such a dynamic behavior and develop the optimizer. You can see in this picture like the Harris-Fox is hunting for rabbit. So what are the behavior of the Harris-Fox? Okay, so there are two types, like the soft end cycle and hard end cycle. That means at first Harris-Fox, this bird searching for the rabbit from the upper direction. So this equation is for that. And when it came in the downwards towards down to the rabbit, then rabbit is moving in fastest position. So that time the Harris-Fox need to be work hard more. So that is known as hard end cycle. So this is we implement the artificial intelligence part into in the artificial behavior of the actually the natural behavior of the Harris-Fox into the artificially, and we make a coding by using those equations. And this is a sine cosine algorithm, is basically the none other than the sine wave and the cosine wave here. And this is the slime mold algorithm. Basically, this is how the slime is searching for the food. What is the, at first, there are the several stages like finding food, exploration, added nature exploration, and all those things. So we make some coding. And after, when you also make some innovative coding, so go for the copyright and the patent. Okay, copyright is basically go for the copyright first, and then your code will be in copyright, and then you can use those things in your upcoming research. So here I can use here. So I am see the this is a code pseudo code of my optimization techniques which I used for this research, and this is the flowchart for that, and how I can merge those equations. So from this diagram, I can show you how we can merge those things. So this is the pseudocode for the another coding, and this is the flowchart for this another coding. And now we test those method for some cases, and we include the renewable energy sources. So here we can use how we increase the efficiency of the photovoltaic system. And those are the mathematical formulas for including the renewable energy sources. So how we can balance the power constant by using renewable energy. So these all are the constant considering the renewable. Here we can consider the solar here. In this experiment, we consider the solar. Okay. And when we consider the solar as well as the electric vehicles, then the equation will be like that. So here we can take the three types of the generating station, like 10 generating unit, 40 generating unit, and 100 generating unit. If 10 power generating unit is connected to the parallel condition, then which generating should be in on and which generating unit should be in off condition. In same case for the 40 generating unit and the 100 generating unit. So those are the unit characteristics for the 10 generating unit, and those are the for the power demand for 10 generating unit. So 10 generating unit data, that is IEEE bus system, it is available for any kind of any research literature review we can get. But from there, we have to calculate for the 40 generating unit, and for 100 generating unit, need to calculate. There is also several another research. Okay. So this is a power demand and the market price. So when we consider the electric vehicle to um, for the better sustainability future, then we can also consider the power also grid to vehicle and vehicle to grid power, and PV means photovoltaic means renewable energy. So here some data for summertime and winter time also. You can use those data for upcoming research also. So this is a medium and large scale power. For medium scale means that 40 generating unit, and large scale means that 100 generating units. So what will be the power demand? This is, and when we use those coding for that system, so I am showing you this is the experimental results which I have done in MATLAB, and this is one of my research work, and this paper is published already in one SCI journal. You can Google Scholar and you can find out this. Some data is available and pseudocode is also available at there, and those are the convergence curve. So every optimizer when we use, we get the convergence curve for the testing purpose. Whether our whether our optimizer is good or bad, so we can easily find out it. So here we can see by using this 100 generating unit, this the bold number is our the best profit. So when we compare our best profit to the another optimization method, we can find out that the our meta heuristic hybrid optimizer have a more profit than the existing hybrid optimizer. Okay, so that we can say that the our experiment is feasible and better than others existing hybrid optimizer. Okay, so we also done the hypothesis test also, the alternative hypothesis and the null hypothesis, and some the statistical parameter test. You know about the T test, P test, and H test, all those things. So those are also, those tests are basically our whatever we generate, whatever we create using MATLAB software, the whatever the optimizer we create in any kind of any software, that is our own coding. So that's it. Is that coding is right or wrong? How we can identify? So we need some hypothesis test for that. So this is the results of the hypothesis, the p value and h value we need to calculate. So now I am conclude my session. Like, we can say the traditional power industry has relied heavily on the coal, oil, and the natural gases, which produce high greenhouse gas emission. So to achieve the sustainable development, and the sector is basically shifting towards the low carbon power generation, smart grid, and the digitalization, energy efficient technologies, decentralized power generation. So this transition creates basically a foundation for the integration clean technologies like solar, wind, hydro, biomass, and geothermal energy, and the role of renewable energy sources in the clean and green energy. Like renewables are central to a sustainable future because it produces no or minimal emission. Solar and wind are the limitless, and technology costs are continuously decreasing, and its reduced dependence on the fossil fuel. Renewables contribution to the sustainable development by the lowering carbon emission, reducing air pollution, improving the energy security, supporting rural economic development like solar park, wind farm, etc. So they also enable the decentralized and community level power generation, which is essential for the inclusive sustainability. Third point is like the electric vehicles, which is a key component of the green transportation. So electric vehicles basically reduce the environmental impacts by eliminating tailpipe emissions, reducing the oil consumption, improving urban air quality, lowering overall greenhouse gas emission, especially when powered by the renewables, EV's adoption supports global climate goals and accelerate the shift towards the green mobility. The fourth point is like the in the interconnection in between the power industry and the renewable industry, including the electric vehicle. When I consider that, then we can say that the EVs increase the demand for the clean electricity. As more EVs are adopted, electricity demand rise. This basically the power industry to add the more renewable capacity to meet the clean charging needs. That the EV batteries also support the renewable energy integration. EV batteries can help the stabilize the grid through the vehicle to grid and grid to vehicle operations. Energy storage during the storage, basically during the peak renewable production. So this enables the better utilization of the solar and the wind energy. Smart grid enable efficient power management like the smart grid coordinate, the renewable generation, EV charging schedules, power distribution and the consumption. This reduces the weightage, ensures the reliability and the supports of the sustainability. And the fifth point is the combined impact on the sustainable development. So basically the environmental benefits are included in this point like the reduction in the carbon footprint, less air and the noise pollution, conservation of the natural resources, and economic benefit are also in that point, like creating of the green jobs, lower operating cost for the consumers like EVs is cheaper per kilometers, and growth of the new industries like battery manufacturing industries, solar EPC industries, charging infrastructures, and etc. Now the last point is the solar benefits. So in this point we can say like the improvement of the public health, better access to clean energy in the rural and the urban areas, enhance the quality of the life through the improvement of the environment. Now I am concluding my thoughts in that way, like the power industry, renewable energy sources, and electric vehicles are basically deeply interconnected pillars of the global transition towards clean and green energy. Together, they drive sustainable development by reducing the emissions, improving the energy efficiency, and fostering the economic and the social progress. So, this integrated approach is essential for the creating a greener, healthier, and more sustainable future. Thank you. Thank you, everyone.
Good evening, all. Now we'll have a 5 minutes break for the next session. Good evening to everyone present here. Myself, Komal Kumari, Assistant Professor of Ramgarh Engineering College. Welcome you all once again to this Faculty Development Program, Day 6, on the topic Recent Technological Developments and Advancements in High Temperature Solar Thermal Technology by Dr. Varun Pratap Singh. As the world moves rapidly toward sustainable energy, solar power stands out as one of the most abundant and accessible resources. However, while photovoltaic systems dominate the renewable energy market, solar thermal technologies, especially high temperature systems, are gaining renewed attention due to their ability to provide continuous dispatchable power, industrial grade heat, integration with thermal energy storage, reduced dependence on fossil fuels for process heating. This makes high temperature solar thermal systems essential not only for electricity generation but also for industries such as steel, cement, chemicals, textiles, and food processing, which require heat temperatures exceeding 800 degree centigrade. High temperature solar thermal technology is no longer a futuristic concept. It is a key driver of the global transition towards clean, efficient, and reliable energy systems. With continuous advancements in material, digital integration, hybridization, and storage, this technology has the potential to reshape industries and strengthen energy security. Now, it is my immense pleasure and privilege to extend a warm and heartfelt welcome to our distinguished expert for today's session, Dr. Varun Pratap Singh, who is a research associate in the Department of Mechanical and Mechatronic Engineering at Stellenbosch University, South Africa. So, we are truly honored to have you with us. With an impressive 16 years of experience in research, academics, and technological development, Dr. Varun Pratap Singh has established himself as a dedicated scholar and a highly respected researcher in the field of mechanical and mechatronic engineering. His association with Stellenbosch University, one of Africa's most prestigious research institutions, reflects his strong academic foundation and continued commitment to innovation. Dr. Singh's work spans across advanced engineering systems, computational modeling, energy technologies, smart mechanical systems, and interdisciplinary research collaborations. His contributions have not only enriched the global academic landscape, but have also supported cutting edge advancements in engineering design, automation, and sustainable technologies. Beyond his research achievements, he has been actively involved in guiding students, publishing impactful work, and participating in international scientific forums, making him a valuable resource for scholars and educators worldwide. Today, as a part of this faculty development program, we are privileged to gain insights from his experience and expertise. His perspectives will undoubtedly inspire us to explore new research directions, embrace advanced engineering practices, and strengthen international academic collaborations. On behalf of the organizing committee, faculty members, and all participants of this FDP program, I extend a very warm welcome to you, sir. We sincerely appreciate your presence and your willingness to share your knowledge with us. We look forward to an enriching, insightful, and thought provoking session ahead. Now, I would request Varun, sir, to proceed on into today's session. Thank you, sir.
Thank you very much, ma'am, for such a kind introduction.
Thank you, sir.
Let me allow to share my screen, please. Let me know if you able to see my screen right now.
Yes, sir. Yes, it is visible, sir.
Okay, thank you.
Thanks.
So, I hope now it is visible to you, my PPT. So, I hope now everybody is able to see the complete PPT right now.
Yes, sir. It is visible, sir.
Okay, thank you. So you already introduced me, and I very much thank you to you all to be presented over here and give me opportunity to share my views about recent technological development and advancement in high temperature solar thermal technology. So I'm associated with STERS Solar Thermal Energy Research Group as an assistant professor at the Department of Mechanical and Mechatronics Engineering, Stellenbosch campus. So I'm also associated with an assistant professor SG in University of Petroleum, India. So, and I'm a kind of a solar thermal guy from last 15 years, and going to share my idea about, you can say, what is going on in solar thermal technology. So this is the content which I'm going to share you. And I hope after completion of my lecture, we will be in a situation where you will get what idea what actually happening in high temperature solar thermal throughout the world. As I did my PhD in lower temperature solar thermal, I'm guiding most of the PhD in medium temperature solar thermal in India, and myself doing work in a high temperature solar thermal. So, and knows the Indian scenario, including IITs and NITs, that they are doing work in a which particular domain. So our India basically focusing on a lower temperature side. So I'm gonna, after this particular presentation, I hope the person either who is working in a renewable energy, any aspect, they might be catching the idea that how they can integrate it with the high temperature solar thermal or solar thermal part of their own research and how their research can become more sustainable. So this is something which I'm going to deliver today. And I hope you see the opportunity where you fit in this particular domain, and maybe not going to change your idea of knowledge, and but you are definitely going to get some experience that what is going in solar thermal domain. So you can say, if I say what are the type of solar energy utilization method, so they are generally divided into two category. One is a direct, another is the indirect solar thermal. Okay, let me choose over here. So you can see direct solar thermal domain basically again further divided into photovoltaic and thermal. The thermal is my part over here for today's discussion. And indirect, everybody knows there's a hydro, wind, bio, wave energy, and ocean energy. That's a kind of a, again, is a kind of a indirect way of transition of solar energy utilizations. So as I mentioned, the solar thermal is also divided into three parts: low temperature, medium temperature, and high temperature. So in Indian scenario, because and worldwide as well, most of the last 20, 30 years, you can say 3 decades, mostly governments and research organizations are focusing on, solar photovoltaic, and we are not getting much funding. But what happened in last 10 years, as the duck curve has been formed, I hope most of the people know the duck curve, means excess amount of photovoltaic generation come in a picture, and then people have to be, those who know about the grid technology, means uh, solar photovoltaic somehow work for a maximum 8 hour duration a day, and then the storage come in a picture, but still it's a kind of a not a win-win situation for every country, those who highly rely on the photovoltaic situations. So again, they are thinking again how they can invest their money in a solar thermal. So I am quite optimistic for solar thermal domain, means of a high temperature especially. So my past experience within a 5 6 years says that okay, now we are getting much grant, not only you can say in India, worldwide. So if you are working in a hydrogen, if you are working in a biomass, if you are working in wave technology, wind technology, even carbon capturing, so solar thermal is a kind of a place where you can integrate your projects. It's a renewable, it's a reliable, it's a sustainable. So that's why my urge to you to see the presentation in this way, that how you can utilize this thing content over there. Okay, so here you can see then this helioelectrical solar energy divided into helioelectrical, like a PV, chemical, and the solar thermal. So today I'm going to discuss about this technology, how you can utilize high temperature. High temperature means generally we are going to discuss most of the thing which is above 400 degrees centigrade. Okay. So if I go for actual scenario of different energy storage technology, which is available right now. So here you can see the things come in a picture means we having a PV, we having a hydro, we having a you can say diesel-based generator system, like we having a nuclear power plant. At the same time, we are having a wind turbine. But somehow this technology, which is centric over here, is going to be my attention for today's discussion. Okay. So high temperature solar thermal basically used for in industry, basically either steam generations, electricity production, water desalinations, and chemical manufacturing. And the latest one is the hydrogen production. From last 1 decade, I see so many people are working in this particular area because hydrogen production, hydrogen utilization, development is a kind of catchy word nowadays. And most of the research grant is also getting attention over there, funding. So there are two major way where you can use the high temperature solar thermal in commercial aspect, which is viable, economical, and even countries like South Africa, which is developing, Australia, which is developed, and most of the country in Europe, Spain, Spain, they are much focusing on this technology. So this one is a central tower system, and another is a concept parabolic trough technology. Okay, so we are getting funding for those technology now. Okay. So I'm just going to check this one. Yeah. So you can see over here. So this is a kind of a tower concept, and this is a kind of PTC, parabolic trough concept. So I'm going to discuss in much detail. Over here, you can see this is a tower concept. In tower concept, basically what we are going to do, we are using temperature of, sorry. So I have to place it down somewhere. Yeah. So in tower concept, we are generally using molten salt of temperature 550 degrees centigrade. And in PTC, we generally going to up to 390 degrees centigrade, 396 exactly. So these are the two technology which are dealing in a commercial aspect, but there's a lot of energy research is going on. So let me explain these things to you so you can create a better understanding with upcoming topics. So generally there are three areas of attention, either in solar tower or parabolic trough. So one is a solar field, where in solar tower generally we having a heliostates which generally catch directly solar thermal radiations and transfer it to a central receiver, which generally divert this particular heat into a molten salt or some other kind of so thermal energy storage fluid, which generally store the heat in the thermal storage system. And this particular heat again used by the Rankine cycle, you can see the power turbine cycle, and we are getting steam turbine and power directly electricity which you can use in a media. And again this fluid is going to change the lose the heat in this heat exchanger, and then getting again the heat from this, and cold storage fluid is again going to get heat from the solar thermal. So previously this system doesn't come with the energy storage, but now as a 24-hour operation is there, so this particular system can operate in a night and even the days where we don't having a sufficient sunlight. You can say up to 7 days or 8 days, some plant actually available with a 16-day power backup, which is actually exist in world. And the another field the same way. Here the same concentrator are replaced by the tower replaced by a parabolic trough systems, but the higher temperature is going to decrease up to 396 degrees centigrade with a particular type of thermal energy storage. Again, this hot storage media where we are going to store this thermal energy, and then the steam turbine cycle, power cycle basically. So if you go, the solar tower look like this. Here, this is one the Redstone Tower, South Africa, which I recently visited over there, and you can see. So these are the solar field concept which I discussed with you. This is a parabolic trough. So I can discuss each and individual component with you, but I'm going to discuss these things in more detail in a later slides. You can see over here, like this is kind of a collector field area where we focus on heliostat or parabolic trough. One group is going to work with those actuators and drives and motors and reflectivity of these reflectors. In this case, heliostat. Another concept is a tower, the central receiver system. Height of tower, thermal energy conversion efficiency of tower is a major concern over there. Another terminology is a heat storage, thermal storage over here. So we focus in this advanced heat transfer fluids, where we are focusing on a different type of fluid which can store a larger amount of heat for a lower heat transfer and with a high thermal cycle up to 10,000 cycles. So they can long last up to 30 years. Huh? And high temp. Give me 1 minute so I can place it over here. Okay, it's not going to go below that. So maybe some of my content going to be covered by this. Okay, sorry, apology for this. And the same time you can see the steam generation cycle is there. This is basically a traditional Rankine cycle. The maximum efficiency of Rankine is around 48.6, which is actually installed in Europe. But still we are expecting that this efficiency can go up to 50%. And there's a heat conversion efficiency system over there. So these are the few attention area of my presentation, which I'm going to cover. You can see high efficiency thermal receiver. We are going to talk about it. How AI system is going to be integrated with this, because everybody is thinking about AI integrations, and they are generally Helios state, which is around 70,000 in this particular solar field. So you have to synchronize 70,000 actuators and motors and drives in the way that this particular receiver get maximum energy. So you can see, oh, there is a cloud, there is a windy situation, there is maybe a low heat transfer rate, there is maybe a very excess heat transfer, and the same time, because load shedding is there, maybe huge amount of heat required. The people of mechanical engineering already know about the governor and how our steam turbine basically works. So in coal power plant, basically, if there is a load demand, so what we do, we generally burn the larger amount of coal. And if there is a low load demand, so what we do, we burn less amount of coal. But in this particular way, how we are going to manage? By putting reflector in the manner that they can transfer maximum heat or minimum heat or the actual desired amount of heat which is required over there. So that's how each and individual area is going to be make a attention for us. Okay, so multi-tower, why we are using single tower? Maybe there's and beam down. So in this particular case, we are using beam up. Means the single central receiver is going to attract all the amount of heat over here, but there's a few more concepts which are under observations, like multi-tower and beam down concentration configurations, which we discuss in our upcoming slide. Then solar thermochemical hydrogen production is a latest area where if you are interested to write a research grant in India, especially ARG's grant or NRF grant or Horizon grant or US grant, so this particular area is going to much attract you. And obviously hybrid solar concentrator is a company or industry demand. So there is a few fluid which are also under observations to utilize in this particular tanks. Okay. So if you go for thermal energy storage, you can see there's a few particular area of domain categorized, which I discussed earlier to you. Maybe attentions gather in this area. Here I'm going to discuss what are the target which most of the companies set for upcoming 2030s. Okay, so these are NREL document where these solar thermal people having that kind of mindset that we are going to put our levelized cost of electricity within the 0.05 kilowatt dollar. You can say 5 cents per kilowatt. So what is the current status? You can see over here. If you focus on the fossil fuels, so from 2009 to 2024, last year, this was the trend scenario. Means why we are using gas, because the huge motivation from government side to procure gas, different, and the coal is going to be stagnant because we already using coal from more than 100 years. So there is not much levelized cost gain. But here you can see the huge downfall come in cost of solar panels, and it becomes really cheap as comparatively any other technology. Wind basically rely on a very high rely on wind velocity. So sometimes it also meets the criteria levelized cost of electricity, but solar PV is a kind of thing which is already getting optimized. And you can see in last few years as duck cover comes in a picture. So the cost of electricity generation is also going high for both renewables. But at the same time, you can see solar tower or high temperature solar thermal is going to get attention, and still we come around 15 cent per kilowatt category. And what we are targeting, 5 cent per kilowatt within upcoming 5 to 6 years. So this is somewhere we are laying over here, and you can see nuclear and geothermal, not very idealistic alternative, but yes, these are the things which are already available in the market. So if I discuss each and individual thing with you over here, so you can see this primary thing is solar field, which attract and concentrate the solar thermal radiation to a central receiver. But solar field, what are our target over here? You can see. So this is a document, is well document from NREL plan configurations for 2030, here 32, and you can see the cost of solar field should be less than $50 per meter square, including glass reflector, including supporting structure, including the motor and drives and technology which generally regulate this particular entire solar field combinations. And the lifetime is above 30 years. So you have to keep in mind, we are focusing on 30-year reliance, okay? And annual efficiency should be higher than 55%. Why we say 55%? Because our thermal cycle basically having a 50% efficiency target. So which is basically you can say Rankine cycle efficiency. So we are targeting much over here, and the concentration ratio is more than the 1,000 sun at a particular point receiver. So if you see the receiver part over here, the I hope my speed is okay for everybody. Please let me know.
Yes, sir.
And am I audible to everybody over there?
Yes, sir. Yes, sir. Yes, sir. You are audible to everyone.
Okay, thank you. And I hope you are getting confidence on these things, and my lecture looks attractive to you guys.
Yes, sir.
Okay, thank you for your feedback, please. So a receiver part, the central receiver. So why I'm discussing this topic to you, there are so many different topics which I can share, but see, in India, we are not working in a high temperature solar thermal, huh? So why we are not working? Because government doesn't having that plan earlier. So from 2022 onwards, now Ministry of New MNRE and our National Research Solar Research Institute is focusing on high temperature solar thermal. Huh? So that's why I'm discussing these things to you. Means so please focus in this way that maybe this particular presentation can be useful for you to write a research grant for future way. Okay. So that's why I'm saying what is going on latest over there. So receiver basically having a mindset of, see, thermal efficiency is more than 90%. We are discussing about electrical drive way of thermal efficiency, which is already 86, 87%. Okay. So the whatever heat we are gaining over here, we are already utilizing up to 86%. So that's why we have target only 90%. Huh? And the lifetime, you can see 10,000 cycle. What is the current status? We already achieved this particular target. Huh? 8,000, 9,000 cycles. There are so many thermal fluids which are working with this particular receiver system. 10,000 cycles is not a very high challenge for us because we are already having this material. So why we have 10,000 cycles? You can see 1 year having working days of around 300. The same time 10 years is 3,000, and 30 year having around 9,000. So that's why we are focusing on more than 10,000. So we are going to meet this particular lifetime criteria. And the cost of per kilowatt of this receiver is going to be around $150 per kilowatt hour. And exit temperature of the thermal fluid when higher than 720. Actually, we are targeting to 800 to 900 in between. But the same time, you can see, and the heat transfer mechanism, we are focusing on the TES thermal energy storage media, which can operate above 800 degrees centigrade. And the power block efficiency should be 50% more than 50. Why we are 50%? Rankine efficiency. I hope when you taught mechanical engineering students, so the maximum efficiency in any numerical should reach around 48.6, not more than that. This is the optimum efficiency which we are reaching right now. And so that's why we are focusing on more than 50% by integration of, you can say, electronics and subsidiary devices, not by the thermal cycle, because thermal cycle already reached to maximum efficiency. And then the dry cooled system should be around 900 kilowatt electric per kilowatt electric. And this target, individual target, is going to be put us in this particular zone. Levelized cost of electricity 0.05. Because see, either you are an economic guy, you are doing a life cycle assessment, you are a sustainability guy. So means you have to see in your area what are actually government is thinking, where they are investing their money. Then you can think about to write a project, research grants, And then obviously, if you are publishing your articles, so that's how you are focusing on this way. So what we are doing, my research group is extensively focusing on this policy type. Same time, we are focusing publication houses like RSCR, where we are focusing on latest issues and latest related to these terminologies. So whenever we write the grant, we are getting it easily as comparatively and not getting much challenge from either you can say Indian part or European part. So I also urge you guys to think in this way, where the government policies promoting your domain of work over there. Okay, and if you go for next slide, this is something you can say is a hybrid model of utility scale photovoltaic. So those who work in a photovoltaic module, which also get integrated in this way. You can see, means same time we are using thermal, same time we are having our previous traditional cycle of Rankine, and same time we are using PV modules with battery storage because we need a constant power supply. So this one is a really optimistic, and I visited 3 plants in South Africa. Uppington is one of them, which having a gigawatt like scale of modules, and the same time they're also having a battery storage. And you don't believe every battery is coming from China. And the whole plant is governed by European companies. So Africa, Morocco, Spain, Cyprus, those places are become kind of place for European to survive their energy need. Just because of, you can say, Russia, Ukraine war inflicts, they are not buying electricity, or you can say directly crude products, including gases from Russia. So what they are doing, they are relying on Mediterranean Sea belt countries from where they can procure electricity directly. And means they already having a pipeline for their coal and their crude oils and natural gas. Now they are thinking to put places wire which directly extract electricity from Morocco, the kind of country, and crossing Mediterranean Sea. And that kind of hypothesis they are working right now, and can directly supply to Spain and Italy. So from Italy, they directly channelize this grid to Germany. That's how they are ambitious right now. And means what I'm saying, what going on right now on a renewable energy domain. So they are not focusing on Australia because it is not practical to put that kind of money over there and feed to Europe again. But that's how they are thinking about to place their investment on Morocco and nearby countries, okay, which are much aligned with the European interest. So these things are going over there. Here you see this receiver basically work on fluid, basically a kind of a liquid over there. But at the same time, we are also working on another fluid, which is solid particles. So what happening over there, we will discuss in a more detail. So solid particle receiver having a, you can say, higher thermal capacity and can operate up to 2000 degrees centigrade. So thermal efficiency, everybody knows Carnot efficiency is directly one more upon a small temperature to higher temperature. So if there is a huge temperature difference, so we can get a more efficiency. So that's why I say we are focusing on this 50% target over there. So these are the kind of fluidized bed combustion. Those who know about power plant, they maybe recognize this particular word. Previously we were using the pulverized coal type system. Now fluidized come in a picture with a very high burning efficiency, and the same concept we are using over here. So I will tell you in detail what's happening over there. So we are using solid particle for making a fluidized bed. So, and this concept is there where we can see those who are working in a biomass and biogas field. So we are basically focusing on either municipal waste or you can say biomass. And again, we are burning this thing over a solid particle receiver. We are storing energy so many ways, so many media are there. And we are also having the particle receivers over here where you can use your these fragmented biomass, and we can either do pulverizations way or fluidizations, and the same time we can use to make a coal, or we can develop a syngas over here in this particular case. And the same time you can use solar particle receivers to make this particular solar thermal field process completely. And again, you can generate either your gasification of by either you need a particular gas for the clean gas to use like a syngas, or you can directly use this gas for other commercial applications. So this is somewhere the biomass gasifier come in the picture. So I just having one figure over there, but the entire research domain come in this area, because when you are working with a syngas production, a commercial level syngas production, the entire process depend on where you are getting the huge amount of energy which needed to be integrated with this biomass, and how you're going to clean this thing entire mashup over there. So you can see the cold tank and hot tank make this particular thing practical feasible. Europe is relying on this particular technology. Those maybe who know about Germany 100% electrification, then their 20-25% electricity come from this particular domain. Okay, so another area of research over here from solar thermal. So if I discuss about the historical development of CSP plants, concentrated solar power, CSP stands for concentrated solar power. So Solar One was the first plant of 10 megawatt, was a commercial pilot plant installed in 1982, and world's largest thermal field developed in 1986. From that time to, you can see now we are focusing on 1 gigawatt operational capacity in 2009. And see, from 1982 to 2009, we are just getting 1 gigawatt. But after that, see, few Solar 2, after Solar 1, Solar 2, when this power plant pilot study work very well, and we understand the claim which we are doing is actually lies over there, and we can do further modifications. So first market analysis, and you can say first installation come over there, then Noor plant come in the picture, and 2.3 gigawatt. And you can see from last few years, from 2009 to 2018, within a 9 year, this capacity increases 670 times. 60 becomes 6.7 operational gigawatt projects, and mostly comes on, you can say, a higher temperature domain. And now I already discussed with you that what we are objecting over here. Right now we cross or bypass, you can say, 10 gigawatt operational capacity, and for 2030 I told you that we are focusing on 5 cent per kilowatt, which going to be make replaceable of this mostly solar PV technology. Because solar PV, those who know in India, that it is morely viable just because of government subsidy, central and state. Mostly center is giving around 30% somewhere, and same time state is also providing 15 to 30%. Somewhere in union territory is going to be 40% up to. But if without subsidized way, it is not very reliable. So government is not having that kind of large interest to provide that kind of subsidy for very longer duration. So maybe in 2030 you see the different scenario where solar thermal start dominating, and majority of research grant is going to be in this particular way. I hope you are able to take that. Mostly publications, mostly research grant, mostly people are now discussing about hydrogen. They don't know about life cycle. They don't know about the entire process, the complication over there. But people say, yeah, hydrogen. This is something which happened when PV come in a picture. Photovoltaic means, because there are huge uncertainty, and for 1 watt we need a 1 meter square area. And see, today this panel become huge success. And the same way, hydrogen is also, we are also focusing on, you can say, betting on a hydrogen. But I'm an LCA guy, life cycle assessment, do things in this way. So I know that what are the complications there. Not very much enthusiastic about hydrogen, but if you are interested, you can also see over there for that kind of target which government is doing. Here you again things, what is the main characteristic of the you can say past and future of the CSP plant. So here you can see we generally divide CSP plants in 3 categories: generation 1, generation 2, generation 3. My recent study where we are going to publish in with the Renewable and Sustainable Energy Review, RSCR, I classified entire solar thermal technology in 4 category. I hope within 1 month you will get this paper online. So in this particular study, we are focusing on a CSP technology. Okay, so CSP, I told you, high temperature. So previously we having, you can say, LFR technology, line focusing, then central receiver system, and then you can say parabolic trough. Now we are generally working with the oil and steam, but you can see in second generation steam and salt, and in third generation we are focusing on salt and particles. So this particle receiver become a one of the latest research area in CSP. And believe me, in India, this making of this particle and making an entire setup is not costlier than 5 lakh rupees. If those who are interested in work in this area, they can install that kind of setup and produce good quality of work and attract government grants within a 1 or 2 year research profile in solar thermal domain. So I generally urge you guys to focus in this way. And you can see the same time the peak operation temperature is quite high. If you are working on hydrogen, see how the people are working with a high temperature solar thermal hydrogen production. I give you some glimpse over here in our upcoming slides. So why I'm focusing over here, you see this particular temperature range we are already achieving over there. And the cycle efficiency for us is right now 42 to 45%, but we are targeting about 50%. Okay. So, and if you go further, here, this slide will tell you, give me 1 minute, please. You can see the LFR line focusing linear Fresnel system, line focusing system, and PTC parabolic and the solar tower. This particular solar tower system is already, see, very economical when they operate above 8-hour cycle per day. So generally they are working with the 8-hour to 16-hour cycle. Two plant, including Noor plant, Morocco, is working with a 24-hour cycle, and they make a latest development where the plant operate more than 160 days continuously. So they become a Guinness Book of World Record, because mostly even coal-based thermal power plant also need a rest. I hope those who are working in this coal thermal power plant, they know that generally we consider only 300 working day in an entire day, not 365, because there is a regular maintenance issues which come with the plants. So solar thermal power plant are much capable to work around that long duration of operations. So you can see already we commercially touch $1, yeah, 10 cent in 2028, 18. And now we are focusing on a much side. So few plant of, you can see the parabolic trough, which are still not very economical, but operational. But yeah, this is a kind of a reliance. So another kind of testing where we are focusing on thermal fluid, not on the technology. So different research are there in economical aspect, that what is the levelized cost of electricity generation for a different type of solar thermal technology. So if I discuss what is actually going on over there. So if we focus on a central receiver system, so receiver geometry is the one part. You can see different way how we can catch maximum thermal efficiency or transfer it to fluid. Either is a you can say thermal fluid, or it's a particle receiver. So these are the few discuss star receiver or the fluidized bed particle receiver, NREL and DLR basically Germany and Fraunhofer Germany. They are working in this particular way. Right now, few are under simulations and few are kind of, you can say, experimental domain. So we put a few solar thermal power plant on 1-to-1 scale, means if this plant is 100 megawatt, so we actually develop a 100 megawatt plant. And now we are thinking about 2 or 3 different receiver technology which are going to test it for at least 1 year. So we are having a complete entire cycle observations over there, that what happening with this particular receiver for a longer duration. So this one is kind of a pilot studies. So who are going to be work for a longer duration to get an actual industrial commercialization aspect. So you can see this one is another molten salt receiver system which I visited individually over there, and this particular setup work with a high temperature of 760 degrees centigrade. So here we are using absorber tip. Those who are working in a power plant, maybe or technology, maybe know this what it is. It's a kind of a water walls which we use in a polarized and fluidized bed in coal-based power plant. But here, these absorber tubes are placed outside over there, and with coating with a very high absorbing material, and solar radiation come in the picture over there. And if you know biomimicry, which is again a new term, maybe you are interested to work in this area. Biomimicry is a kind of bio-inspired thing from nature, and maybe you know about the flower. I show you one slide in my later stage. So where we are doing previously research with a very normal geometry, which we know by generally calculation, we having calculation for those things like circular pipe and cylindrical pipe, blah blah. But now we are focusing that, okay, what inspire us from nature. So we are trapping solar thermal in the way that the temperature generally going above 1000 degrees centigrade, and we are even melting steel in this particular way. So even in India, I hope you know about 2-3 research institute over here. They are working very well above the temperature of 1200 degrees centigrade. They successfully melt Mount Abu over there. They having a solar furnace where they are melting steel, and this become a very good news for researchers who are interested in this area. So working over there. So these are a few more. You can see hybrid thermal receivers where we are having a different geometry, and those are the papers which are published and cited over there of their references. So they are either working on flower geometry. You can see flower over here this way. These are leaves, and this one is central receiver, which generally operate above 1200 degrees centigrade. And again, this geometry over you can see, and is a central comb receiver technology. So I'm not going to much detail over there, but you can see that there is a lot of research going on a receiver side. And if you go for again, so I mentioned you that another part is a different type of thermal energy storage fluids. So those who know heat transfer fluid, they are become much older in our area, just because we are focusing on a higher temperature of more than 1200 degrees centigrade. So here heat transfer fluid generally start breaking their or losing their chemical property or heat storage property, or they're not very operational for 10,000 cycles. So what we are doing, we are focusing on particles which are relatively cheaper, non-toxic, and much friendly with environment. So they are easily decomposable and doesn't having very high cost of operations and very reliable. So that kind of different particle we are using over here, I'm going to discuss in much detail so you can understand what chemistry is behind this and how we are using these things. So here is NREL. Basically, we are having a central particle receiver facility. What is going inside over there, how particle is receiving, moving from one side to another side, and how we are shedding particles from upside to make it fluidize. And the same time, we are concentrated through heliostat over here, this one, and it is going to receive more than 2000 degrees centigrade temperature, which is very quite high mostly. And these particles are much operational now. So this another way is focusing over there. So you can see here we having closed loop cycles. Those who are focusing on closed loop, this is again another area of study of closed loop. So like closed economy. So my focus is on a CSP side of receiver. So you can see closed loops working, that how much this particle not only receiving heat or by one side, but they are operating so many simulation that okay, are these particle are much capable to retain for 10,000 cycle, or what is the chemical chemistry, what is the you can say chemical characteristic composition or decomposition happening over there with the particle, with the reservoir boundary, with the heat transfer media over there. And these things are going on. You can see we having a 12.5 megawatt central particle receiver facility again at DLR basic Germany. So that kind of testing we are doing over there, and they are inviting people either from India, you can go for by government grants over there, and they also having their own research program where you can file the application that you are interested to visit their facility, and you can move over there with their fundings. Okay. So another thing, if you go for more detail, so this kind of see the closed loop receiver, we having so many different kind of particles where we are either moving downflow, and downflow means top to bottom, upflow means bottom to top, and horizontal flow. So that's how we are flowing different particles. Which particle is good in which category? See how the research is already gone, and what is the particle characteristic melting point. You can see few particular more than 2000, more than 3000, and we are using them very efficiently. Okay. And right now we are focusing on the how much cycle they are going to be work for there. So you can see few research articles over there, and this is two-way working. One is you can say direct sun method, and another is off sun method. So in direct sun, what we are going to do, the solar radiation come in a picture. In off time, the solar radiation doesn't come in a picture. So what we are doing, we having a hot storage. You can see the heat transient media and cold storage media. So generally, we also having a hot solar reservoir over here. So what happened over there when you start working, with solid particle receiver, and it start pumping over there, and getting a solar receiver, solar heat gain. So this high temperature solar storage uh, generally store these particles over there, and this heat transfer basically took place over here, you can see, and this become a cold storage. Now what happened when sun is not available? So this particular reservoir of hot storage start losing the particle over here and still operate, make it operational, you can see over here. And again, this cycle is not working right now, you can see over there, and we store cold storage or the particle over here to in cold storage. Why in cold storage? Because cold storage also having a very high insulations and lose only 1 degree centigrade in a 1 day. So that is the heat transfer efficiency which we already have. I mentioned that on, so this particle bed size having a around 20-meter dia and 10-meter to 20-meter height, you can say. In this particular case is 30-meter. But you can see, means I am storing something at 1200 degrees centigrade, and 1 day operation efficiency is I'm going to only lose 1 degree centigrade of this particle receiver. If I didn't operate it for a multiple day, still I can renew this particular cycle, okay, but not with this high efficiency. So you can see how solid particle are working right now. So these are the few work going on. And if we see the closed loop CSP, so again, I mentioned you that how these things are going on, and different absorber combinations, and you can say hot particle compositions come in a picture. So I hope few of you know that we are also using super carbon dioxide, supercritical carbon dioxide cycle over here, being a heat exchanger, because it operate within a 30 to 32 degree centigrade temperature. Those who may be interested to work in this area. So why I'm saying supercritical carbon dioxide, because it take change, its triple point is around 32 degrees centigrade, which is very low comparatively steam. So it is also, we don't having any actual plant of megawatt capacity, but right now this is a 100 kilowatt setups which we having a pilot study scale right now. So you can see again another thing is coming in a picture. We are changing Rankine cycle through Brayton cycle, but here we having a working fluid is a carbon dioxide. Okay. So I already discussed that we are using multiple tower instead of a single tower. So few actual plant of true scale means 1-to-1 scale is already operational, and we see that this particular way of working is quite good on so many aspects. Like you don't need a huge large field. At the same time, you don't have to think about a single receiver efficiency, and don't have to be work with a very high temperature range, because when these thousands of reflectors just focusing on a single receiver, so operational challenge and material challenge come in a picture. But when we divided it into different receiver, so obviously your that kind of challenge reduces. But another bad thing come in a picture is, because you operating on a lower temperature range, your thermal efficiency is also going to decrease. So as we reliance on a higher temperature material, so if you're having good material and single time high investment solutions, so go for single tower receiver. If you think that, okay, we can plan one by one, so multiple tower system is quite good. And what about the beam down system? This one is a beam down concentrator system. Few studies says why you are making tower in a central way, because tower working depend on transfer of fluid from lower side to upper side. Again, if you think about this, in this case is not 100-meter, but the previous tower, this one is 100-meter height, because there is a huge solar thermal field. I mentioned 40,000 to 70,000, 25-meter square each heliostat is there, which is going to focus over there. So obviously you need a central sphere which is placed at quite high height to make them more efficient. And so for 30 years, what I'm planning to put my particle or thermal fluid up to 100-meter height. You can imagine what is the pump work input over there for 30 years. So the next concept come in a picture that, okay, why we are thinking about up down cycle. So make some beam down mirror over there, which directly reflect heliostat to a downward directions. And here we having a central receiver, and this receiver can be transferred molten salt from lower temperature to higher temperature. And exactly this setup is made by China. So I having a good relation with so many country, like Germany. I know people over there, but they are working. There, I am also working with them. Australia, South Africa, USA. But the last 1 decade, I see China. They are so China doesn't stand anywhere last 10 years back in solar thermal, and now they are leading with a margin where the other country doesn't even come to near the by them. So they installed a huge capacity, either central receiver or this one, beam down setup. And when the other company think or country think about, okay, pilot electricity of 1 megawatt, what they do? They place 50 megawatt single pilot plant over there. You can see in the Xinjiang provinces, they place this particular 50 megawatt setup, and it is completely operational or not single. You can see other one is there. So yeah, people like me is also getting attracted by their work. That okay, and I'm also focusing on continuously focusing on their study and tracking down that what they are doing actually. So means yeah, your neighbors are also doing huge research in this area, and this is something where you can see that advanced thermal energy storage fluid lies. So if you are looking, so what we are doing here, you can see is a time over here from second, minute to hours operation. The same time, if you are looking for a 1 kilowatt to megawatt or gigawatt setup. So I personally recommend this kind of table to you, that which fluid you choose, thermal energy storage fluid or media, and what is the transmission and distribution cost is, what is the operational cost rate, what is the you can say installation cost of that kind of setup. And so you can see even lithium ion battery is already surpassed by molten salt technology. So those who know that how lithium ion battery become commercialized in the automotive sector, because everybody use the technology, but the same time, see lead acid battery, then flow batteries, and where we stand for molten salts. So if you are looking for a megawatt pellet plant, especially above 10 megawatt, so most welcome for doing your research in molten salt category. As you know, being an Indian, we need a huge energy, and as we also having a 2047 targets to become one of the leading country, as we are going to be celebrate our 100 years of independence. So means this molten salt is going to be get much attracted over there, you can see. And so means 100 megawatt gigawatt, this technology is going to be retained over there. Okay, so this study shows you that okay, if you are working in this way, so where molten salt come in the picture. So maybe you see lots of study, lots of people are working on this particular way. But if you are looking for, you see, hours operations, so this technology is much reliance. And in a molten salt, I personally say particle receiver. So solid particles come in a picture in a new technology terms over there. So this is something which is the actual figure right now of thermal energy storage. So what is going on over here? You can see there are physical heat storage and chemical heat storage, which is further divided in this way. So generally, I discuss chemically heat storage. We are not focusing on this area because a lot of chemistry come in a picture. So being a mechanical guy, I am much comfortable, and mostly people are doing energy research in this way. So everybody knows there's a sensible heat, latent heat, or thermochemical heat storage. So what happening over there? So previously we are thinking about sensible heat storage. Sensible means heating change take place at a single phase, and latent heat phase change take place at a constant temperature. So PCM was there of much attention. People think about organic, inorganic, acidic, and polymers. Now, most of the, from last 5 to 6 years, or you can say 1 decade, we are working on absorptions and chemical reactions. So I hope you know the absorptions and adoptions. So when the particle absorbent is basically covered by absorbents, so it's known the adsorptions. And when this absorbent suck the absorbent, it becomes absorption. So absorption is kind of thing where both come in a picture together. So, and having a very high thermal capacity, I hope you understand that, okay, this particle also going to get attracted some thermal capacity, having some thermal capacity. The individual particle who are within the our media is also going to be absorbent, is also having some thermal efficiency or capacity. So that's why these options become a very high heat efficient or using a very high thermal capacity media where the basically people are working. So if someone is working in a thermal domain, so I personally recommend to see this particular area. for a future production, or you can say their research. And this is something which is, capacity of what is going on at TS. So you can see PCM previously we are focusing on there, but when we discuss about energy density, so you can see absorptions is quite high over there. And if you are working with solid particle receivers, so you can see chemical reaction come with a picture of 10,000 cycles. So they already touch this particular area, and you can see the temperature is above 800 degrees centigrade we are discussing there. So right now we are focusing, we are already having 7,000 800,000 cycles, but if you are looking for a more energy density, more cycles, so we have to surpass this particular way. But we are not obviously focusing on ethanol, we are thinking about the solid particle over there being a solar thermal part. Okay, so what is going over there in advanced TS? So you can see in solar thermal chemical conversions, what we are doing, generally, this is kind of a very fundamental thing, but if you're having a two particle A and B, what we are doing, we are passing them through, you can see the solar concentrator directly storing this heat in a composition this way, and become an endothermic reactor. And AB is for the segmented into A plus B, and some heat going to be stored over there in A and B. So we having two particle storage facility, which is thermally charged. And when we do exothermic reactions, they release their heat in the way that we can further utilize the power. And then again, this low fluid become AB and again goes to the endothermic reactor chamber. So AB storage, A plus B storage is kind of high temperature side, and is a low temperature side. So that's how we are doing thermochemical conversions. So there is a hydrates, hydrox, carbonate, and oxides, which we are right now focusing. There are few already simulation study which proven, and few research grant under I hope Horizon grant, Europe, one of the biggest grant, already attract few research. NREL and DLR already having this project with them. Okay, so. And if I say that another range of TS technologies, so this one where we are focusing in chemical looping, you can see I already mentioned this loop things over there. So right now, this is something which are focusing high temperature and hours and days and month operation. So chemical looping is under observations of, you can say, technical and industrial parts. So there are a few challenges of material erosions, pump erosions, and continuous operation of these particular cycles, because chemical also having a very high sensitivity in terms of reactions at high temperature. So this was something, if metallurgy people are sitting over here, they can understand this thing much better than me. So we are looking for that kind of resistive material which can be part of this one. So if you are looking any grant which is focusing from MNRE and DST, you can focus in this way, that okay, where you're are you having that kind of coatings materials with you which can retain, or metallurgy things where the chemical looping come in a picture. Okay, another thing, so this one is a kind of a hydrogen production. So yep, solar thermal people are also much enthusiastic to produce hydrogen. So we are doing this research not only in India, throughout the world. DLR, NREL people so are also focusing this way. So they're having that kind of a high setup efficiency, because where we are operating with a very high temperature in 1200 degrees centigrade and above. So these systems are practically possible, but and a very high amount of hydrogen can be produced this way. So we having thermochemical metal compositions over there. So you can see the hydrogen production either can be done with cerium oxides, where we having two-step cycles, which generally operate between 400 to 2000 degrees centigrade. I mentioned you concentrated solar already reached this particular temperature, but metal composition is quite challenging over there. And another cycle, which is relatively low temperature from 400 to 500 degrees centigrade, work on a copper chloride hydride. So basically it's a hybrid cycle and produce very good quantity. So I hope the people know hydrogen gas. So quantity and quality and rate of production of reliable gas is a challenging thing, which this particular technology already surpassed. So you can say why we are not placing that kind of plant, because till now the concentrated solar is not that economical at a lower scale. Means if you're looking for just 100 kg per hour hydrogen production or electric capacity. Generally, we use kg to measure the hydrogen because it's much concentrated, or sometime in liter. So if you are looking for that much low quantity, this particular technology is not very reliable. So means concentrated solar thermal. You need to be producing, some tonnage capacity. Then only these things can come in picture. So another thing, but yeah, research is going on in this domain also. And then AI integration, I mentioned you, is also over there. Why we are doing AI integration? I mentioned that the tower having a central receiver system having either thousand of parabolic trough or 40, 50,000, sometimes 70,000 of heliostats. So obviously operation of those heliostat in a that synchronized manner where people doesn't get interacted directly with the system. So AI come in a picture. Okay. So another topic which I just want to cover over here is additive manufacturing and challenges over there. So right now my research in India is focusing on medium temperature solar thermal, where I'm guiding my PhD students on concentrated solar thermal. The same time you can see over here what I'm going to present, that how people can think by biomimicry. Why I'm mentioning these things to you? See, what I experienced in last few years, as I mentioned, from my undergrad, I'm a solar guy. In masters, I did my solar thermal work in solar thermal. In my PhD, I work in a solar thermal. In my postdoc, I did work in a solar thermal. I am a faculty and working on a dedicated solar thermal domain. But what I realized, in within a 3 year, not more than 5 year, within this particular time, my entire industry going to be changed. Means if I am out of touch from last 3-4 years of my domain, it become very new for me. It just look like you can see computer people, means either they have to work on Java, SQL, and .NET or different technology. The same thing happened with us also. Means if you are working on some thermal fluids 3 years back, now you feel that okay, if you are, no one is giving you grant on this particular thermal fluid, because already everybody is dig dive, everybody know what actually happening over there. So you can publish paper, but you can get grant from very good research institutions or industry, because they already having every facts about this particular thermal fluid with them. Characterization is done, commercialization is done, actual TRL level technology is already developed. So what you are going to do there? So means why I'm saying means that kind of challenges already come in a picture, means on our human thinking level. So what I'm introducing over here, if someone of you may be thinking in this manner that okay, everybody doesn't having very huge research grant with them, or maybe doesn't having much support from government or institution level, so they can think in this integration of this kind of way. Okay, so what I'm suggesting you guys over here, and this is a very new topic, huh? So maybe you know that how nature and human thinking work over there. So if I say this is gonna to be maybe you guys to think, okay, means what we can take inspiration. Either you are working in any area, but this particular presentation is going to help you over there, huh? See how we think about the bone. Means in a, pardon? Sorry, anybody saying something?
Every participant, please mute yourself.
Do anybody having any questions so I can answer if you feel so? Or should I continue?
Sir, you continue, please, sir.
Okay, thank you. So, being a human, we think, okay, how bone look like. Even in cartoon, we think how bone look like, how we think heart look like, and miss so many things are in the market. Even when you offer the bone to a dog, it's also look either is biscuit or something. It look like this, but actually, how nature think bone is that much complicated inside. Okay, so if nature designs something, it is you can say very much having complications and develop with very huge time taken. Huh? So see how we think in a very fundamental manner. Means the place you are sitting anywhere, irrespective, you can see the table is a kind of a rectangle things. Your stool, your chair, your room, your tall, maximum your booklet, maximum thing with make with some fundamental figures: rectangle, square, triangle, circle. even our complicated engines also having follow the same geometry, है And but there is a one company like I hope everybody knows this thing, Elon Musk, SpaceX. So where NASA doesn't even develop the thing, Elon Musk do one incredible thing. They develop each entire company, SpaceX, within a 10-year period, where the nation fails. Being an Indian, you can blame either government or research or blah blah anything, but you can see from last 27 year we are dedicatedly working on a jet engine, but still it's a very shady condition for us, doesn't having anything. But the same time the guy developed a engine called Raptor, and the same time being a mechanical engineer we can understand when we having that kind of approach. Okay, we have a Rankine cycle. Now we have to improve the Rankine efficiency. It's a 28% only. So what we do, we put reheater, regenerator, evaporator, economizer, air preheater. I hope you understand what I'm saying. Multiple thing on a particular cycle make it more complicated, non-realistic, non-reliable. So that's how people think in the initial way. Best example is Rankine cycle. How many modification we did and still doesn't touch 50%. So what the same thing they did, they come with the Raptor 1 engine in 2020 and place each and every turbocharger, air preheater, economizer, everything over there. And then suddenly they realize, don't follow this thing, go with nature design. I told you what it is. And the same time you can see, initial engine was in 2020 having a weight of 3,600 kg. Now they remove each and everything and make it as simple as they can, and it become 1,700 kg. The previous thrust was 185, and now it's a 280. You can see around huge jump is there, and they put it on multiple scales. Okay, where NASA, ISRO, another research organization are not doing. So what is the first principle? You can heard him that he says, okay, I work with the first principle, I work with the first principle. And see, this is a kind of a nature thinking what we can apply in our area, whatever research you are doing. See, even at a larger scale, that's how we think about skyscraper. And when we say, oh, we are going to make it something different, how it look like, it's still very reliable things way. See, when we design, we heat it, we treat it, we beat it. But how nature design never do these things. So what I am saying, if you see, so nature inspired and human inspired design, we generally don't use a global non-renewable resources. Why I'm saying global non-renewable means the thing which may work in India doesn't work in South Africa and definitely not going to work in Europe. They having their own standards. But when nature thing is always look for locally available. And see, when you say sustainable, reliable, locally produced, everything come from nature design. Okay, the tricky word, the catchy word, whatever you are thinking, something come in a natural domain. Okay, so from past 5 years, I am doing a LCA. I also myself give you a new selection index, which is a completely my IP, you can say. And getting a huge recognition for this selection index. You can see my research article over there, published with a very renowned Q1 journals. And then I also see that, okay, LCA having their own limitation. Everybody dedicated their 10 years or 20 years in LCA, and now they say, okay, LCA having their own limitations. So why I'm saying, because still there is something which is missing in nature aspect. Okay, so see, mostly human design are extractive, where the nature do the renewable thing. We always think in a linear flow, waste production, but yeah, nature think in a circular way. So circular economy, circular loop, circular things. From where this word come? From nature, definitely. And our manufacturing funda is a heat, beat, and treat. And the same time, that's how we do subtractive manufacturing most of the time. And nature do additive manufacturing. Now, maybe you people are very famous being a mechanical additive manufacturing. Now we are thinking about additive. We are adding things in otherwise previously we are subtracting things. So, and there is a blueprint approach, means there is a design, you must do things and not adapted. So maybe become a fragile. The same time, generally what nature do, the locally attempted solutions, adapted and resilience. And generally they make the things, creates conditions which basically follow the conductive lives. At the same time, we think, in a predictable manner. What is this predictable manner? We think about chemicals, cost, analysis, availability, mechanical treatment, reliability, operation things, blah, blah. But nature think only about these constituents, much rely on carbon, hydrogen, nitrogen, oxygens. I hope you know how environment have been developed, how people the hydrocarbons element come in our picture. Means either it's a environment, either is a living or non-living species. You can see the integration of nature. So why I'm saying nature choose a much reliable thing. Okay, being in a earth guys, we are much focusing on you can say gold, diamond, and thing. But do you know if you are looking for a guy who is traveling in the universe, so you never go for gold and diamond things. You always look for wood or carbon things, because being a human being, getting carbon in a universe, not think about on the earth, in a universe, you will never get a tree if you're traveling to the universe. There are diamond larger than sun. There are gold completely you can say earth kind of celestial body made of gold, earth kind of celestial body made of diamond, but there is nothing like a that kind of celestial body made of wood. So you're already having that kind of composition in earth, but I don't think so any society having a wood based currency. So what I'm saying, see, our way of thinking is quite complicated and depend on the rare thing, rare, which is rare to us. But if you think in a universal aspect, so what is rare in the universe? Wood. What is a rare thing in a universe? So I hope you understand what I'm saying, being a first principle. So if I go beyond it, so that's how, see how much complicated is basically individual bones, how much detail they look like. Why I'm saying maybe you are focusing on your research in the way, superficial way. If you are still feel that there is a opportunity, so think about the nature way, how nature think about this particular topic. So maybe you are getting much attraction. See, still what we are doing, nature-based design. I hope those who maybe from additive things, they know now we are focusing on Neuralink is the company, again by Elon Musk. They are doing that kind of sensation. So if I extend this thing, those who are working in design and simulations using CATIA and ANSYS ProE softwares, so maybe they are much aware with the word generative design in manufacturing. So generative design is a new words which going to be replaced and having a potential to replace designer, or you can say those who are doing simulations. Why I'm saying, I'm just going to run 2 video over here, and parallelly I'm going to put my voice over here so you can understand what's going over there. See,
What if you could come up?
this video.
What if you could come up with thousands of options for a single design without drawing?
Okay, let me. I hope now you are able to see the video. Please let me know.
Yes, sir.
Okay, so you can see, if being a human we design, this is the simplest way we design, but just ANN come in a picture, and now you're having thousand option where ANN and CNN choose different way of design, which you can choose to design your objects. And you can see generative design, additive manufacturing, make it more reliable. People can sell this thing that's because it look very shiny, but at the same time much reliable. If you are doing this Baha thing, I hope you know. So LiDAR making design over here, you can see we are putting sensors, load sense cell, and that's how you are getting intensity. And the same time, you can give the generative design command. This is my load or panic situations over there. Just develop something which is practically developed, can be developed, and you get design. Here you can see Boeing is using airframe modeling or an initial internal part of the plane, which is developed by generative design. Previously, it having a huge load and made of aluminum. Now they are using cheap material, less weight, having high strength. And you can see they are replacing 9,000 kg weight to 4,000 something weight, just half. So this is a kind of a generative design which is available in market. Already Autodesk having this software features over here. You can see, means if you are going to use these things, means this is something which is really near to, you can say nature, how nature think with so many permutation combinations. And another example over here, I'm just giving you. So here is a bike which needed to be make one particular instrument over here, equipment over there, and how parallelly few things are going to be integrated. See, if you are looking three things, what is the object which you are looking for? So they are looking for suspension things. I integrate over here. You have to see what are the obstacles, what are the load in the under calculations. And as you say, ground load is there. See how many study type are there, what method you are going to choose. Additive, milling, forming, and is give you thousand designs which you want to choose. And based on your initial calculations, they give you that kind of trend. And if you say, okay, these are the final 5 design, here you can see this video is available on YouTube. See, these are the 5 design which worldwide having a different manufacturer, because Autodesk already having a manufacturer CNC capacity. They know who can develop this thing. And you can see over here, they give you strength, different things, how much capacity this particular instrument, the particular things having, and who can develop throughout the world for this particular part to you. And this again, additive, completely available. See, I'm not saying something futuristic. This thing is already working over there, no? And that's how you can develop your part. You know who's the manufacturer, what capacity they have, what the process they are going to build, develop in this particular part, how many times it's going to take, what is the final cost for me, and see if this particular bike having that kind of particular instrument over here. So maybe going to be attract more people. And generally, being a human, we are not capable to design in this way. See, so that's why I'm saying nature inspired thing. Okay, those who may know biomimicry, bio inspired things, this is something where we are also focusing. Okay, being an engineer, mechanical engineer, and dedicated to solar thermal. So these are the few solar PV guys are doing. What they are seeing that, okay, there are a few plants who generally follow, sun trajectory. So this is okay. If we see there is a PV panel and we want to optimize our electricity production. So what they are doing, they are thinking about bio-inspired artificial the photosynthesis integration with this particular column over here, where they are doing systematic simulations, how it work and what are the efficiency they can achieve. They also place some, you can say, prototypes with a very small scale. You can say it's only in a millivolt, but at the same time, they are seeing what is the efficiency which they can achieve. And this how they are doing the thing. So it's a very initial level, but yeah, they are able to extract that kind of cells, which generally follow sun trajectory. Another thing which I told you, see, previously we are thinking in a very flat manner for our CSP design, concentrated solar power receiver. See how this receiver look like. It look like, you can say, central receiver, but having a cylindrical aspect over there. And we are developing something which attract or catch solar thermal radiation, but the geometry which we are using is a none of any natural object is made by this way. Okay, but at the same time we having a flower over here, so many type of flower. I can see every flower life depend on a solar radiation, and the same time there are the different part, very high sensitive part, and always having different shade color. Why this particular plant having different shade color? Being a mechanical solar thermal engineer, I can say they having different concentration ratio and absorption capacity. You can see light color, relatively dark color, and you can see much concentrated black color with a high thermal absorbability. So because this particular part having a pillars and pistons which needed to be a particular temperature, just birds also having that kind of temperature for their sensitive parts. So means we know that there are the egg cells which have to be at a particular temperature, and that's how plants regulate their movement and the same time geometry. So why are not focusing that kind of nature inspired design for our receiver? And I mentioned you, people are working in this way and focusing in this geometries. Previously I show you few bio inspired design for receiver, And now they are previously we are just having a 400 to 700 degrees centigrade, and now by following just of the geometry, we are discussing about 2000 to 3000 degrees centigrade temperature zone. So you can see only making bio-inspired design with our previous existing testing facility, the thing completely changed. So if you are a designer guy, if you are a metallurgy guy, please take some inspiration from nature, and maybe these things make you good and maybe helpful for you. So this is somewhat my presentation look like. I hope you enjoy. And now we can having a discussion part over here. If you are looking for any questions, so I'm happy to answer you guys, please.
To all the participants, please ask our respected teacher, Dr. Varun Pratap Singh, sir, if you have any query regarding this topic. You can share your thoughts also if you wish.
Yes.
All the participants, if you have any query regarding this topic, you can ask our respected teacher. If you have any problem regarding your mute button, you can also ask in the chat box also.
I also on my chat box. So if anybody is interested to discuss anything, and see, my presentation basically discuss about what is going on in my area, but I hope you also get inspiration from my presentation, that how, so few takeaways, maybe what government think in this area, and whatever you are doing research, and what you can do with the latest way, please. So this is something which I just want to conclude for you guys, please. Sir, I think you are not audible. Can you please?
Sir, our participant Nilesh Kumar sir had expressed his gratitude towards your explanation. Dr. Abhijit
Yeah, I see.
Devnath sir
Thank you,
also.
Nilesh.
Thank you. Respected Dr. Varun
you.
Pratap Singh sir, on behalf of the entire organizing committee of our faculty development program, I am Pallab Das, Assistant Professor of Ramgarh Engineering College. I am expressing my heartfelt gratitude uh, for this exceptional keynote address. Thank you very much, sir.
Thank you.
Your international perspective, profound knowledge, and insightful explanation enriched this session and provided great value for all of the participants. Thanks a lot, sir. Thank you once again for inspiring us. Uh, uh, Regarding your busy schedule and the geographical distance, but still you are with us. Thank you very much, sir. And we hope this kind of session will continue, and we will get you in our next sessions also. Thank you very much, sir.
Thanks to all of you to give me opportunity.
Thank you, sir.
Nice to talk to you, sir.
Thank you, sir.
Bye, everybody. Take care.
Okay, to all the participants, the exam link for the online test will be provided at 6:30 p.m. on the WhatsApp group. You will have 1 hour, and along with that, you will also get the feedback link for this program, feedback Google form for this program. You will surely add the feedbacks for this faculty development program also. Thank you very much, everyone. We are getting a small break, and you will get the online test Google form and feedback Google form in the respective WhatsApp group. Thank you very much. I'm just sharing the links soon. Thanks a lot.
Thank you, sir.
To all the participants, I'm also sharing something with you that our validatory session for this FDP program will be started at 7:30 p.m. sharp, and at 8 p.m. the session will be over. So we are requesting you all to join that session. That is the last phase of this FDP program. Thank you very much, everyone, every teachers from different backgrounds, different colleges. Thanks a lot, sir. And we will soon giving you the link for feedback and online test on the WhatsApp group. To all the participants, the online test and feedback Google form will be sent to you, the respective WhatsApp group, and you can rejoin at 7:30 p.m. in this meet. So now you can leave, and you should surely join at 7:30 p.m. for the validity session. Thank you very much. I am just sharing the uh, online test link and feedback link at 6:30 p.m. and at the WhatsApp group.
Okay, thank you, sir.
Okay, thank you, sir.
Thank you all. Thank you all. Does everyone get their online test and certificate? You can text in the chat box also.
Yes, yes, yes.
So now we are just starting the valedictory session for this enriched faculty development program, the 6-day faculty development program on climate and energy, innovation for a sustainable society, sponsored by AICT Atal Academy and organized by Ramgarh Engineering College. I, Pallab Das, on behalf of the organizing committee of Ramgarh Engineering College of this Atal FDP, concluded that it gives us immense pleasure to acknowledge you all that we had done this FDP with a very suitable manner. Obviously, there are certain glitches, network glitches are there, but still we had completed this FDP with immense pleasure. The program served as a comprehensive platform for enhancing knowledge, expanding perspective, and building capacity in the critical domain of clean energy, climate resilience, and sustainable technological innovation. Over the 6 days, the FDP witnessed active participation from faculty members, research scholars, industry professionals, and technical experts from across the country. The distinguished resource person representing premier institution like IIT ISM Dhanbad, BIT Sindri, KLE Tech University, CSIR Simfar, international universities, industry organizations, and government bodies contributed significantly by delivering high quality, insightful sessions. The 6-day AICT Atal Faculty Development Program on Climate and Energy Innovation for a Sustainable Society concluded with outstanding academic rigor and practical relevance. Each session was thoughtfully designed to strengthen participants' understanding of clean energy transition, alternating fuels, climate technologies, and sustainable development. The program not only expanded theoretical knowledge but also connected every topic to real world application crucial for India's clean energy mission. Beginning with green energy transition, uh, policy, technology, and practice, participants gained a foundational understanding of how global and national policies shape the roadmap for sustainable energy system. This created a strong base for all subsequent sessions. Sessions on net zero carbon goals and carbon capture and storage, CCS, established the scientific and technological relevance of reducing greenhouse gas emission. Through expert insights, participants learned about advanced CCS techniques, carbon utilization pathways, and how academy industry partnership can accelerate India's journey towards net zero emission. The lecture on emerging renewable energy technologies like solar, wind, hydrocarbon, and alternative fuels were at the heart of this FDP. They highlighted the latest advancement in fuel cells, hydrogen production, hybrid renewable system, and indication of clean fuels in industrial application. These sessions directly aligned with the program's central theme by demonstrating how innovation in fuel technology can drive climate resilient. Practical exposure was further enriched through detailed discussion on sustainable energy, systems, smart grids, and energy efficiency in building and industries. These talks showcased engineering design strategies, demand side management, digital monitoring tools, and future-ready energy infrastructure, areas critical for implementing sustainable societies. We are very much pleased to inform you all that we are very much delighted that you all attended this program, this FDP schedule, these sessions, because those people who had given this type of they had shared their PPT, they are very much enriched with knowledge, and we are very much thankful for Atal also to give us this opportunity, to give Ramgarh Engineering College to this opportunity to develop this kind of FDP program. The session on climate resilience, urban infrastructure, connected energy science with environmental planning. Participants understood how smart cities, climate resilient buildings, and sustainable waste and water management contribute to long-term societal resilience. The circular economy in energy and climate system session emphasized material recovery, resource optimization, and waste to energy strategies, highlighting sustainable industrial practices that reduce environmental burdens. In addition, lectures on policy, economics, and regulations enabled participants to link technological innovation with economic feasibility and government frameworks, ensuring the practical viability of clean energy solutions. A major highlight was the session on AI and IoT for sustainable energy management, where participants explored cutting edge tools for predictive maintenance, automated energy distribution, intelligent monitoring, and optimization algorithm. This session perfectly aligned with modern technological trends and offered futuristic perspective on energy management. Collectively, each session, whether focused on alternating fuels, hydrogen energy, policy intervention, carbon capture, or digital energy system, contributed to a cohesive learning journey. Every lecture reinforced the importance of integrating technological innovation with environmental responsibility for achieving a sustainable society. The organizing committee extends sincere gratitude to AICT Atal Academy, respect dignitaries and eminent speakers, and enthusiastic participants. This FDP stand as a milestone in our continued commitment to promoting clean energy research, academic excellence, and sustainable energy practices. The knowledge shared, collaboration formed, and ideas generated during this program will inspire further advancement in climate and energy innovation at both national and global scales. Thank you very much, every participants, and I will surely share the PPTs of the last day sessions to the respective WhatsApp group. Thanks a lot. I guess everyone get their certificate from the Atal portal. We are very much pleased to inform you that. And now I am handing over the mic to our coordinator and co-coordinator, Dr. Ashish Narayan sir, academic in charge of Ramgarh Engineering College, and a dedicated person who had given us much pleasure to form this kind of FDP program. Thank you very much, sir. And I am now handing over the mic to Dr. Ashish Narayan, sir, co-coordinator of this FDP program.
Thank you, Palla sir. May I audible to all of you?
Yes, sir, you are audible.
Okay, thank you for the nice introduction about me, sir. So today I will start the validity session of this FDP, Atal FDP for 6-day program. I will like to share my gratitude to our respected Chief Partner, Professor Dr. D.K. Singh, Vice Chancellor, Jharkhand University of Technology, Partner Dr. Mohit Chatterjee, Vice Chairman, Techno India Group, Advisory Committee Member, Professor Dr. Pankaj Rai, Director BIT Sindri, Dr. Sudipto Chakravarti, Director Techno India Group, Dr. Vishnu Chattopadhyay, Director TIG Jharkhand, Dr. Sarvani Roy, Principal Ramgarh Engineering College, Dr. Najmul Islam, Vice Principal Ramgarh Engineering College, respected guests, distinguished speakers, esteemed colleagues, participants, ladies and gentlemen, those who are participating in this particular FDP, 6-day FDP, good evening to all and all. It is my privilege and honor to stand before you today as we bring this remarkable program to a formal closure. Over the past 6 days of the FDP program named Climate and Energy Innovation for Sustainable Society. We have shared transformative ideas, exchanged meaningful knowledge, challenge our assumptions, and include new perspectives. This validatory session marks not merely the conclusion of an event, but the beginning of many promising possibilities born out of the insight we have gained together. This event drives their true value not only from the agenda they follow, but from the people who bring them to life. I extend my heartfelt appreciation to all our esteemed speaker and resource person. Your expertise, clarity of thought, and inspirational lecture have enriched every session and motivated us to pursue for excellence. To all participants, your enthusiasm, active engagement, and eagerness to learn have been truly commendable. You are the region this program holds its significance. I hope you leave today with renewed motivations, enhanced skill, and a strengthened sense for the purpose that will guide your future endeavor. A very special note of gratitude goes to our organizing committee, whose dedication made this event a success. Mr. Pallav Das, Dr. Ayani Nandi, Mrs. Komal Kumari, Mr. Arunava Datta, Mr. Kamal Ahmad, Mr. Piyush Mandal, along with the supporting staff and dedicated volunteers. Once again, on behalf of a coordinator of this FDP, 6-day FDP, I once again thank each one of you for your presence, your contribution, and your positive energy. With that, I formally declare this voluntary session closed, and also I would like to thank to give me Atal, AICT Atal, to give me this opportunity to provide our college to conduct this FDP, 6-day FDP. Thank you. Wish you all success and wonderful evening. Thank you to all of you once again.
Thank you very much, sir.
Thank you, sir.
Dr. Ashish Narayan, sir,
Yes, sir.
Thank you very much for your lovely conclusion. And now, last but not the least, we are here because of the person, our motivator, Dr. Najmul Islam, sir, our Vice Principal of Ramgarh Engineering College. Always try to promote us, always try to motivate us for doing such kind of activity. Thank you very much, sir. And now I ask Dr. Najmul Islam, sir, and I am handing over the mic to Dr. Najmul Islam, sir, to say something to again inspire us.
Thank you, Pallav, sir. A very good evening to everyone present here. On behalf of the Institute Innovation Council, Ramgarh Engineering College, it is my privilege to deliver the vote of thanks at the conclusion of this 6-day AICT-sponsored Atal Online Faculty Development Program 2025-26 on Climate and Energy Innovations for Sustainable Society. First and foremost, I extend our heartfelt gratitude to AICT and the Atal Academy for granting us the opportunity to host this meaningful program. Their continued commitment to academic enrichment and capacity building has played a crucial role in making this initiative possible. Our sincere thanks to all of our eminent speakers, resource persons, and experts who shared their valuable knowledge, innovative perspectives, and deep insights on climate change, sustainability, renewable energy, and technological interventions toward a greener future. Your contribution have broadened our understanding and inspired every participant. I express deep appreciation to Professor Dr. D.K. Singh, Honorable Vice Chancellor, Jharkhand University of Technology, Ranchi, our Vice Chairman, Sir, Deputy Director, Sir, Principal, Faculty Member, Organizing Committee members, and the Institute Innovation Council team for their constant encouragement, coordination, and dedicated efforts behind the successful organization of this FDP. A special note of thanks goes to all the participants from various institutions across the country. Your engagement and active participation throughout the sessions made this program truly enriching and interactive. But last but not the least, I acknowledge the technical and administrative teams whose efficient support ensured that every session ran smoothly. As we conclude, let us carry forward the knowledge gained and continue to contribute to a cleaner, smarter, and most sustainable society. Once again, thank you all for your presence and support. Good night.
So it's the end of this thorough session. Thank you very much. And we will like to acknowledge you if some more events will go on in our college. Thank you very much, everyone, and a very sweet evening for everyone. Thank you very much, sir. Now everyone can leave. Thank you. Thanks a lot.